All right. So the unit that we're about to look into is on rational expressions and equations. Okay. Now, you've heard the word rational before, probably in multiple contexts. But in math, you've probably related it most to rational numbers, a rational number. So, as opposed to an irrational number. So I want to talk a little bit about that first. What does a rational number look like? What type of number is rational as opposed to irrational? Okay, yeah, so 1, 2, 3, 4, 5, etc. Those are natural numbers. Those are rational. Yes, those are examples of rational numbers. Yep.
They don't have repeating decimals.
Okay, almost. They can have repeating decimals. They can't have non-repeating decimals. Okay. What do they kind of look like? What do we have? Yes? No? What do we have to be able to write them as? A rational number. Yes, I heard someone say it. Okay. So a rational number is a number that can be written as a fraction, a over b. Okay, and then there are some conditions, okay? So a and b both have to be integers, right? Positive and negative whole numbers. So pi over 2 doesn't count because pi is not rational, okay? And then additionally, b cannot be 0 because we're not allowed to divide by 0. Okay, so but basically that's the gist of it though. You have to be able to write it as a fraction. So that's why we talk about like terminating decimals, repeating decimals. Those types of decimals can be written as fractions. So those are all rational. Okay? A rational expression okay, so first let's focus on this word expression. An expression in math. What's an example of an expression, a mathematical expression? Hey. If you're not sure, I want you to Google it. Take out your phones, Google what is a mathematical expression. Okay, so you actually Googled a rational expression. I just want to talk about what the word expression, a math expression. What's that? Yes? Yes, so think of something with algebra, right? Variables are involved, but there's no equal sign, right? So think like 2x plus 1 is an algebraic expression, okay? There's lots of different examples, but it doesn't have an equal sign. That's exactly it. A rational expression, think rational means fraction, expression means algebra. Rational expression is like an algebraic fraction, okay, basically. But specifically, more specifically, it's an expression in which both the numerator and the denominator are polynomials. Okay, so for example, something like this, when we talked about polynomial functions, so we know what polynomials are, hopefully, x cubed plus 4 over 2x plus 1. That is a rational expression because it's a fraction, numerator, and denominator are both polynomials. Okay, so this would be an example of one. Okay, there's lots of them though. Even just 1 over x is a rational expression. Okay? We can come up with more. I do want to talk about some non-examples because I think when you look at the non-examples, it helps to clarify exactly what the definition of these things are. And mostly the non-examples would be expressions that are not polynomials. So something like 3 over the square root of x, that is not a rational expression because the square root of x is not a polynomial. Okay, it's actually a radical expression. Okay, or something like 2 to the x over x plus 1. Okay, also not a rational expression. Why is this one not a rational expression? Yes?
Because you can't have exponents.
Right, so you can't have a variable in the exponent position, right? A polynomial function, the variable is always in the base. This is actually an exponential expression, okay? So those are some non-examples, but we're really mainly going to be talking about these ones over here, okay? We're also, towards the end, going to also talk about rational equations, and that's basically an equation, so now we have an equal sign, that includes at least one rational expression, okay? What we're going to focus on today is we're going to review factoring because since these all involve polynomials, factoring is going to be one huge step in the process of working with these expressions. Okay? So in this course, the only factoring that is expected is 2 types. Taking out a greatest common factor and factoring a difference of squares, and that's it. So all that stuff around trinomials of the form ax squared plus bx plus c, that sort of stuff, you will not see questions like that in this course. Okay? In fact, if this is the last math course you ever take, then this will be the last time that you have to factor anything until you're a parent and you have a teenager who's taking grade 10 math, and then you're going to have to help them with their homework. But yeah, that's it. So I want to review how to do that. Okay? All right, so that's all we're going to do today. We're not actually going to cover any of the course content today. We're just going to review factoring because it's such a key step to solving these problems. Okay? So when you are looking at taking out a greatest common factor, you want to look at each term in the polynomial and sort of separate it into parts. So if you have this guy over here, 6a squared y minus 12a, each term is made up of a number, an a, and possibly a y. So you want to kind of separate those 3 things. When you're taking out a greatest common factor, you first want to look at the numerical coefficients, the 6 and the 12, and say, okay, what's the greatest common factor between 6 and 12? 6, okay? So 6 is going to be part of the GCF. What about between a squared and a? A. They both have one factor of a. So I can take out an a. And then what about the y? No, I can't take that out. Okay, why not? Yeah, the second term does not have a y. Okay? So first thing you're going to do is take out the greatest common factor. And then you're going to put a set of brackets beside it. Now here's something key. The number of terms inside the brackets, when you take out a greatest common factor, needs to match the number of terms in the original polynomial. So there needs to be 2 terms here. Okay? The first term is going to be the original first term divided by the GCF. So think, what is 6a squared y over 6a? It's ay. Yeah. The 6's cancel, right? A squared over a is just a. One factor of a cancels, so like the squared goes away. And then you're left with ay. And then minus the second term. 12a divided by the GCF. So 12a divided by 6a is what? What's 12 divided by 6? 2. And a divided by a? A divided by a is 1. Yeah, so that's it. This is factored. Okay? Hold on a sec. Yes, okay. So I want you guys to practice these ones. I think I want to do this one together, though, because there is one other point that I want to make that we haven't talked about yet. Okay, so I want to try this one together, and then you guys can do the rest. So the point that I want to make is that when the first coefficient is negative, like this one, typically we factor a negative sign out with the greatest common factor. Okay, so if you look at 26 and 4, what's the greatest factor between those two numbers? 2. But instead of factoring out a 2, I'm going to factor out a negative 2. Okay, and then between x cubed and x, how many x's can I take out? 1. Because this one has 3 of them, this one has 1 of them. I can only take out 1 because they both have 1, right? Or at least 1, I should say. And then between y and y squared, how many y's can I take out? 1. Okay, so this is my GCF. Okay, now think about this. What is negative 26 divided by negative 2? 13, yeah. What is x cubed divided by x? X squared. And what's y divided by y? Just 1, so that's it. That's all that's left, 13x squared. Okay, and then here, what is 4 divided by negative 2? Negative 2, yes. So this sign has to switch as well. Think negative times negative makes positive. Okay, what is x divided by x? 1. And y squared divided by y is y. So minus y. Okay? So I'm going to give you guys a couple minutes. I want you to try the rest of these. Yes. It should. Thank you. There we go. All right, that's pretty good. First real mistake today happened 23 minutes into the day. All right, well, in that case, let's talk about factoring a difference of squares. Okay, so I want to talk about what a difference of squares is first. And it's actually exactly how it sounds. So difference, what math operation do we think of when we hear the word difference? Subtraction. And squares means we're looking at two perfect squares. Okay, so for example, you might see something like x squared minus 9. Okay, this is a difference of squares because there are two terms. They are both perfect squares. X squared is x times x. 9 is 3 times 3. And there is subtraction between. Okay, so this is a difference of squares. When you are factoring a difference of squares, they always factor into the product of two binomials. The first term in each binomial is the square root of the first perfect square. So if you think, what is the square root of x squared? That would be x. So x and x, that's the first term. The second term in each binomial is the square root of the second term, which is 3 and 3. And then one of these is addition, and one of them is subtraction. Doesn't matter which is which. Okay? So let's try one more. Let's say I have that. Okay? If you recognize that it's a difference of squares, and that's one of the most important things that you can do, Then set up two sets of brackets. Okay? What is the square root of the first term? 5. 5 and 5. What is the square root of the second term? 6y. Okay? One of them's addition, one of them's subtraction. Okay? All right, actually, let's do these ones as well. I'm going to skip this one because we did something very similar to this one already. I want to talk about these two, though. Okay, so take a look at the middle one. Is this a difference of squares? No. 8 is not a perfect square. 288 is not a perfect square either. X squared is a perfect square. Okay, so here's the thing. We are doing two types of factoring in this course, greatest common factor and difference of squares. Okay? You may have a question that has both. And if it has both, you need to take a greatest common factor out first. So when you are going through the factoring process, the first thing that you want to ask always is there a greatest common factor in this polynomial? And if there is, take it out. Once it's out, you can keep going and say, okay, well, what do I have left? Is that a difference of squares? Okay? So between 8 and 288, what's the greatest common factor? 8, right. Okay? And then 8 divided by 8 is just 1. What's 288 divided by 8? 36. So minus 36x squared. Okay? Now, if we look at the binomial that's left, we have to ask, is that a difference of squares? Yes. 1 is a perfect square, and 36x squared is a perfect square. Okay? Now, here's what I get a lot of when I ask this type of question. I'll get people go x plus 6 times x minus 6. Because you focus on this guy. Okay? Problem is, x is not the square root of that, and 6 is not the square root of that either. So really mechanically think, okay, what is my first term? It's 1. What's the square root of 1? 1. And what is the square root of 36x squared? 6x. One of them's plus, one of them's a minus. Okay? So that's that guy. And then let's do this last one that I'm going to get you guys to practice on. Okay? So 81x to the 4 minus 16. Is this a difference of squares? Yes, it is. Okay, so I'm going to set up my two sets of brackets. Okay, what is the square root of 81x to the 4? 9x squared. So that's the first term. What's the square root of 16? 4 and 4, plus and minus. All right. Am I done? It's a loaded question. Usually when I ask that question, it means I'm not done. Okay, so what we have left are two binomial factors. Yes? Say that again? Here, we're looking at this guy. Yeah? Okay, so can I keep going here? Yeah, probably. That's probably why I asked that question. Okay, so once you factor, you kind of want to do another check-in and say, am I done? And what you're looking for is one of two things. Either a greatest common factor or a difference of squares. Do we have either of those in what's left? Yeah. What do we have? Difference of squares right here. This is another difference of squares. Okay, so that over there is a difference of squares. Okay, what about this? Can we factor that? No. A sum of squares cannot be factored. Okay, so we always put something like that in. We always put a sum of squares in because I'm trying to trick you, right? This is a sum of squares. It can't be factored. You're done. Okay? But that just stays as is. This guy can be broken down. Right? So the square root of 9x squared. Yep.
Why can't you do it on the first one?
Okay, so we'll talk about that in a second. Okay? I'll tell you why. Okay, so here this is 3x and 3x. Square root of 4 is 2 and 2, and plus and minus. Okay? Now, the reason that a difference of squares can be factored and a sum of squares can't sort of comes down to, whoops, I'm going to add a page. Comes down to factoring a trinomial, actually, of the form ax squared plus bx plus c. Now, I know I said we weren't going to talk about this, but I do want to answer that question. So whoops. Why can't a sum of squares be factored? Okay, so here's what it comes to. If you think of, let's say, x squared plus 9. Okay, this is a binomial, but we can artificially turn it into a trinomial by writing it like this, x squared plus 0x plus 9. Okay, it's still the same thing. It's not actually a trinomial because we don't have any x's. But if you remember back from grade 10 or maybe grade 11 how to factor these are factorable. Think of this as a coefficient of 1 when you can find two numbers that multiply to a times c, to 9. And they have to add to b, which is 0. This is impossible because the only things that multiply to 9, if we start with that condition, you can do 1 times 9 or negative 1 times negative 9. You can do 3 times 3 or negative 3 times negative 3. Okay? None of those add to 0. Whereas, if you try and factor this, x squared minus 9, if you think of this as 1x squared plus 0x minus 9, now you're looking for two numbers that multiply to 1 times negative 9 and add to 0. And we can find two numbers that do that. The two numbers that do that are 3 and negative 3. Okay? So this is why a difference of squares is factorable. A sum of squares is not. Okay? I'm not going to go much further with this because you don't have to factor trinomials in this course. And so I don't want to confuse people who don't want to go there. But if you want to come talk to me about this and review this, please do, because actually when we start to solve equations, you could use this strategy if you want to solve equations, but you can also use the quadratic formula as well, which just avoids this altogether. Okay? Okay. So I want you guys to try these questions. And then actually after that, there's a bunch of practice questions for you to do on the next page that's just a mix of everything. And that's going to be it for today. That's all we're doing. I do have a riddle to give you that's just more practice with factoring GCF and difference of squares. So I'll give that out as well, but that's what I want you to work on. Okay?